Today, a little different. We're not going to do one warm-up problem, we're going to do two, because there's sort of two fun things. And one of them is more a word of warning, and one of them is just a fun problem to do. So we'll start with the first one. So we'll cover up the sort of the longer one so you don't get too distracted. So, all right. Determine if the following is true or false. F of x is x squared. G of x is x minus 2 raised to the power of negative 2. And the derivative of f times g is the derivative of f times the derivative of g. All right, what's your gut feeling? True or false? False. We should check, just to be careful. All right, so let's take these functions. So we have f of x. That's the function x squared. What's f prime of x? 2x. Now g of x, we want to write this in a way that we can actually work with this. G of x, I can write that as 1 over x minus 2 squared. All right. And on a side note, just because it'll help speed it up, in general, we showed this last time, but maybe we didn't celebrate it enough. If I have the derivative of anything squared, that's 2 times the function times the derivative of the function. And we actually worked that out. We didn't, say, hey, look at this cool thing. This is going to become so natural, and about a week from now, we won't even say, oh, that's remarkable. But okay, just for reference. So, g prime of x. Well, according to this, it's a 1 over, so you can use the reciprocal rule. So the derivative of g prime of x says you take minus the derivative of what's downstairs and divided by what's downstairs squared. So that's the reciprocal rule. So since it's a function squared, that would be minus 2 times x minus 2 times the derivative of x minus 2, which is 1, divided by x minus 2 squared, x minus 2 to the 4th. And, okay, we'll just leave it for there for right now. If we need to simplify it later, we will. So we can conclude that f prime of x times g prime of x, well, negative 4x times x minus 2 over x minus 2 to the 4th. I just multiply these two derivatives together. All right. Now let's look at f of x times g of x. So the derivative of f of x times g of x, well, that's the derivative of, and what would it be? It would be x squared over x minus 2 squared. Now, how do we take the derivative of such a thing? It's a quotient. So we take a quotient rule. So the quotient rule, which we learned last time, that's why we can ask this question today. You take the bottom term, x minus 2 squared, times the derivative of the top term, 2x, minus the top term, x squared, times the derivative of the bottom term. Well, that's 2 times x minus 2 times 1, following the rule we did over here. All over the bottom term, squared. So this will become x minus 2 to the 4th. Well, what can we do? Well, we can do a couple things. Certainly, we can factor out an x minus 2, because that's common to both. And we can also factor out an x, because that's common to both. Let's see, we have x minus 2 to the 4th. Let's see what's left. So from the first term, what do we have? Well, we have x minus 2, and we have a 2. So that'll be 2 times x minus 2. The second term, what do we have? Well, we have a minus. We have an x, because we only pulled out one x, and there are two x's here, so there's an x, and there's a 2. So that'll be 2x. And if we see this, inside that's 2x minus 4 minus 2x. And the 2x's cancel. So that means there's a negative 4 in x minus 2, and in x minus 2 to the 4th. So let's just check. The question was, do these match? And the answer is, yeah, they match. Okay, so now at this point, you're probably like, my faith has been shaken here. What are you trying to teach me? Is this a better way to take derivatives of products? And the answer is no. What I'm trying to tell you is be careful. This is a true statement, but, this is a big but, probably shouldn't capitalize the word but it's a coincidence. So be really careful. So this happens, the biggest challenge that we have as calculus instructors is that people have they come in with all these beliefs. And the beliefs are built off of things that they saw. They saw, oh, I remember I saw this one crazy time. You wouldn't believe it. When I took the derivative of f prime, I want to take the derivative of f times g. And it was just f prime times g prime. And therefore, I am convinced that it's true all the time. You see, they're taking a coincidence, a one-time occurrence, and saying, well, that must work all the time. So whenever you have something, you should not be satisfied by saying, one example is enough. You should say, no, I'm highly suspicious. My calc instructor said, trust nobody. So you can't convince me with just an example. I have to have a couple of examples, and I get to choose the examples. That would be at the bare minimum. But in math, here's the crazy thing. If you give us 1 billion examples, we're still not satisfied. We want it to know it works for everything. So whenever we give you a formula, it's been vetted and checked, and we're going to explain why it works for everything. So just be careful. And don't rely on coincidences. Be suspicious of everything. All right. Okay, now the fun one. So you have started a new job raising tribbles. The amount of tribbles that are produced is dependent on the number of tons of quadrotriticale grain that gets put out for feeding by the following formula. The number of tribbles based on the amount of quadrotriticale is e to the 2q minus 32e to the q plus 84q squared minus 50 plus q times pi to the 8th, and then that's how many tribbles you get. Now you're trying to determine the amount of grain q that your predecessor set out for the tribbles. Usually there's a monitor which displays information about the numbers of tons of grain, the amount of tribbles, and rates. Lots and lots of rates. So you're looking at all these derivatives to get information. And each readout that comes has the right units. Now the monitor, unfortunately, is mostly broken. Cutbacks, all right. So you can only read one thing. And the only thing which you can read states that there's 360 tribbles per ton of grain cubed. So use this information to determine the amount of tons of grain which was being used for the tribbles. All right. So my guess is we should probably look at what's inside the box, because that's going to be important. So it says 360 tribbles per ton of grain cubed. Now, how can we use this information? The units. What is that telling us? It's a second derivative? Well, think about third. Maybe a fourth now. I don't know. Fifth? No. Do I hear 7? Okay. So let's think about it. So we have data, but see, it's not just a number, it's a number with units. So the units tell you something. So think about what's happening here. So our function t is a function where the units are triples. Our input is based on the amount of quadrotriticale that you've put in. So what we have are the units of the output over the units of the input cubed. Now in terms of your derivatives, what happens is every time you take a derivative, you put an extra factor of your input in the denominator. So the first derivative would be tribbles per ton of grain. Your second derivative would be tribbles per ton of grain squared. Your third derivative would be tribbles per ton of grain cubed. So what happens here is that this information is saying I have a third derivative. So we can translate now. So the clue is to realize that this actually has useful information. So we've been told that t triple prime of q is equal to 360. All right, so now that's our translation. Now we translated a statement into something we can work with. So given that we know the third derivative is equal to 360, what should we do next? We should probably find that third derivative, which of course if you want to find the third derivative, you start with just the derivative. So we're going to start with our function. So here I'll just rewrite our function. E to the 2q minus 32 e to the q plus 84 times q squared minus 50 plus q pi to the 8th. Now you might say, wait a second, are we allowed to use q as a variable? And the answer is yes. Because variables really are stand-ins for symbols. It's just these are things we don't know. And we oftentimes use a name that makes sense. So we're using q because it's quadratically. It's hard to say that word, quadratically. But anyways. So that's why we're using q. It doesn't matter what we call it the variable. All right, so let's go and take our derivative. Now, e to the 2q. We've actually taken that derivative before, but let's just remind ourselves. The derivative with respect to q of e to the 2q, what is that? 2e to the 2q. Okay, good for reference. All right. So t prime of q is 2e to the 2q. Okay, what's the derivative of the next term? Minus 32e to the q, because the derivative of the exponential function, you get back what you started with. All right, how about 84q squared? 168q. Derivative of the negative 50? Gone. And q pi to the 8th? Well, right, don't we need to bring the 8 down though? Yeah. See that 8, that's sort of a misdirection. Because it's like, hey, you feel like, oh, I should use my cool rule. But remember, we only use that for the part that's varying. Pi to the 8th is a constant. So it's really a constant times q. So when you take that derivative, you get just that constant back. All right, 1 down, 2 to go. T double prime. All right, what's the first term? Derivative of that? 4e to the 2q. Okay, good. Next term? 32 e to the q. Good. Next term? 168. All right, pi to the 8th? Gone. It's a constant. Constant. All right, 1 more to go, because we said we need third derivative. All right, derivative of 4e to the 2q? 8e to the 2q. Derivative of negative 32e to the q? Minus 32e to the q. Derivative of 168? 0. Okay, so now we've gotten our third derivative, and we say, okay, next step, set that equal to 360. Well, So someone has suggested, maybe take the natural log of both sides. Is that a good suggestion? Now you're probably thinking, he's not writing it down. I think the answer is no. Well, it would be good to take a natural log of both sides. Because it's totally natural. It feels right, right? Because it's like, hey, I've got this q upstairs. I want to bring it downstairs. I want to free it. But what's wrong right now? Why can't we take natural log? The reason we can't take a natural log is this part right here, that minus sign. Natural logs do not work well with things being added and subtracted. They work wonderfully, amazingly well with multiplication and division. But once you have a subtraction, it basically starts breaking down and it can't make progress. So unfortunately, we can't do logs yet, but we'll get there. We'll get there. A log is coming. And, you might say, you can imagine being the captain of whatever facility is doing this. So you could say it's a captain's log. But anyways, we digress. All right, someone said divide by 8. Well, let's see what happens. That's e to the 2q. 32 divided by 8 is 4. And 360 divided by 8 is 45. Okay, that's good. Now at this point, what can we do? Now, factor, that's an interesting choice. Now, does it really factor? Because this is like e to the 2q. Wait, I thought we had to have like a square. Oh, it is a square. You're right. See, that's e to the q squared minus 4 e to the q minus 45. So you really can think of this as something to factor. Now, if you feel uncomfortable, just replace e to the q by some other symbol, say a big x. X squared minus 4x minus 45 equals 0. And then you're like, okay, I can factor that. That's perfectly fine to factor something like that. Does it factor? I love how trusting you are. Yes. It does. All right. But I appreciate that you're like, I trust my instructor. He would never give me anything mean. That's not on an exam. Okay. All right. So what do we need? Well, we have that e to the q term. Okay, and e to the q. So we need two numbers that multiply to negative 45 and sum up to negative 4. Yeah, negative 9 and positive 5. So you can get e to the 2q. Then you get plus 5 e to the q minus 9 e to the q. That's negative 40 to the q and minus 45. Now, at this point we can say, okay, either e to the q is 9 or e to the q is negative 5. But one of those we can probably knock out. We can knock out negative 5. Why is that? The exponential function is always positive. It's a beautifully optimistic function. You can't get that function depressed. No. You give me a bunch of negative news, I'll still be positive. Maybe not very positive, but I'm still positive. I always find the silver lining. Okay, so that says we need e to the q equals 9. Now what do we do? Now we can do natural log. And the reason we can do natural log now, there's no addition or subtraction going on. It's just one term equals one term. Let's free the q, and we take the natural log, and we end up deciding our final answer is that q equals natural log of 9. And so there is our answer. All right, well, that's good. A good problem. Okay, well, on to today's topic. So one of the things that we're going to keep doing is just sort of saying, let's think about what the derivative is. Well, let's think about it in a slightly different way. And let's think about it in even yet a slightly more different way, but they're all more or less common themes. So the derivative can be a rate of change. Now, oftentimes when you start thinking about derivatives, early on we kept saying, oh, remember it's like, think about it as a tangent line. So you're like, okay, derivative is the slope of a tangent line. Derivative is the slope of a tangent line. And oftentimes that gets stuck in your head to such a degree that you forget, oh, derivative actually represents something even more broad. Now, the connection is not so big, a gap. It's a natural thing to say, because a slope talks about the change in y, which is your rise, over your change in x, which is your run. So a slope is a rate of change. And so when we talk about the slope of a tangent line, we really should think of it, okay, so a derivative, it's a rate of change. And what you're trying to understand is the following question. I have two things. I have, if you always draw a function here, you can have your machine. I'm not very good at drawing functions, but I always draw the same machine. They're not very fancy. So what happens? The thing is, you have x, and out comes f of x. What you're trying to ask is the question, well, what happens if I change something? So you're saying, okay, what happens if I don't like this x, but I choose an x right next to it, x plus a little bit? You know, and I put that in. The question is, what happens to the output? What happens to that? In other words, if I change a little bit in a positive direction, does my function go up? If I change a little bit in the negative direction, does the function go up then? And how much? If I'm changing x by, 1 or 2 at a time, does the function change by 5 or 6, or maybe 20 or 30? I mean, that's what we're after. So we want to understand what's happening. How does one variable change as you change the other? But it's still, at the heart, it's the same computations. It's just sort of saying, let's make sure we understand that the computations can mean multiple things. So let's try some examples. So given that y is equal to x squared plus x, what is the rate at which y changes with respect to x when x equals 2? Now, whenever you see the word rate for the next couple of semesters, you should almost always think, that sounds a lot like derivative. So think of rate meaning derivative. So now you have y changes with respect to x. So I want to talk change in y, which is dy, and then with respect to means like dx. So this phrase, the rate at which y changes with respect to x, our notation says dy dx. So really it's asking about the derivative. All right, well, the function x squared plus x, do we know that derivative? What is it? 2x plus 1. Okay, so this is how the y changes with respect to x at an arbitrary x. So if I want to know what's happening when x equals 2, I could say find dy dx when x equals 2. This is one way to write this notation. There are other different ways to write it. You could also have written this, for instance, as y prime of 2. But in either case, they both represent what happens at the specific value of 2. The answer is 5, because you take 2 times 2 plus 1. If I want to find the rate of change at 5, or again, you could write this as y prime of 5, what would that be? 11. 2 times 5 plus 1. So whenever you see the word rate, start thinking derivative, derivative. Okay. Now, do an example here. Given a circle with radius r, what is the rate of change of the area of the circle with respect to the radius for a given value r? So let's think about this. So first off, what is the area of a circle? Pi r squared. That's good. So area is equal to pi r squared. So we're after a rate, which means a derivative. What derivative are we after? Well, we want the change of area with respect to radius. So we want to say, how does A change as we're changing r? dA dr. So the rate derivative of area with respect to r, radius. Well, what is dA dr? Two pi r. Okay, so that's the first question. There's a second part to this question. How can this be interpreted geometrically? So this is an interesting question. So let's think about what's happening. So think about your circle. Imagine you can draw a circle. So here we go. Here's our circle. It has radius r. And now we want to know how it changes. So you think about, okay, when I'm thinking about changing, you think about a small perturbation. So I'm going to just sort of go r plus a little tiny bit. And so then I'm going to say, well, what happens? Well, I take that little tiny bit all the way around. And what's the change? Well, the change is this little tiny strip. Right? That's our change. Now the question is, how much area is there, approximately? What's our intuition? Well, when you're looking at this, what part of the circle are you looking at? The circumference. You're looking at the very edge. What's the circumference of a circle? 2 pi r. We've seen 2 pi r before. And that's the circumference. In fact, this is not a coincidence, because what's happening is, if we think about it, if I want to see how much I'm perturbing the area, well, the answer is whatever the circumference is. If I have more circumference, then when I perturb, I'm going to get more area. See, if I had a very small circle, very tiny one in here, the same perturbation would add a little bit of area, but not as much as if I had a larger circle. So that the amount of perturbation, the size of how much my area changes, is directly correlated to how big my circumference is. That's what's changing at the very edge, that small change on the edge. All right, let's try another problem. Suppose that we're given a sphere with radius r. What is the rate of the change of the volume of the sphere with respect to the radius for a given value of r? So let's start by saying, what is the formula for volume of a sphere? 4/3 pi r cubed. All right, and what are we looking for? Looking for a derivative. What's the clue that we're after a derivative? You see a rate of change. Rate of change is secret code for derivative. We're learning to pick up our signals here. But what specific derivative? Derivative of what with respect to what? Volume with respect to radius, r. So that is dv dr. So let's take that derivative. What do we get? 4 pi r squared. Now, there's a question, how can this be interpreted geometrically? Well, suppose you have a sphere, and you say, okay, I want to perturb it. So we do that same thing as we just did, which is, say, oh, let's just push it out a little bit. And then we put a little tiny bit of change. We say, okay, well, given that I've just put this little bit of tiny change, how much have I really increased by? So what's the thing that's right on the very edge? The surface. So the surface of the sphere is essentially the part that's right there to be perturbed. It's like you take the surface of the sphere and you multiply that by a small bit of change. Do you know what the surface area for a sphere is? It's 4 pi r squared. So there you go. All right. Well, there's circles and spheres. Let's try a little bit of physics. So our little bit of physics is pretty straightforward for now. And once we get into, say, multivariable calculus, well, then we're going to have a lot of fun. All right. But for now, we can say, look, one of the things we often care about is motion. How are things moving? So we're going to have a set of functions. So our first function, we're going to call it position. And for whatever reason, the notation that we're going to use is S. S of t for position. I'm not really sure why, but that's okay. It's just a symbol. So S of t is position. Now once I know where I'm at, the next thing I want to know is, okay, how am I changing? In other words, how am I moving? So if I want to know how my position is changing, what's the thing I look at? I look at velocity, but what is that coming from? It's the derivative. So if I want to understand how something is changing, look at its derivative. So I take S of t, which is position at time t, and I take its derivative. Because it's the derivative, that's answering the question, how is the position changing? And we call that the velocity. Now there's two things that oftentimes are closely linked, but we have to pay attention to, which are velocity and speed. They're very similar right now, but you have to be careful. What's the difference? Velocity, you can be positive or negative. Speed, you can't be negative. So you can't have a negative speed. So the way to think about it is that speed is your size of your velocity. And what's going on here, and this is an idea which we'll say several times, it shouldn't be a very big idea, which is to say, in fact, when we think about numbers, for example, think about numbers as positions, there's always an orientation, because there's this number line, and you can go right or left. So you have positive infinity and negative infinity. So velocity is storing information that's sort of saying there's two pieces of things I want to know. One is, how fast am I moving? But the other thing about velocity says, am I moving to the right or am I moving to the left? So that velocity has an orientation, or if you will, it has a direction stored in. Now, it's a very simplistic direction, left or right. When we get up to multivariable calculus in a year from now, we're going to be like, oh, we can go in all sorts of directions. But that's a year from now. All right. Well, now we have our position, we have our velocity, and the next thing we do is say, okay, let's think about how velocity changes. If we want to know how velocity changes, what do? We take a derivative of velocity. So if I want to see how velocity changes, that's the derivative of the velocity, but of course the derivative of the derivative gets us the second derivative of position. And we call this acceleration. So acceleration says, how is your velocity changing? So you can have positive velocity and negative acceleration, which is to say that, I'm moving forward, but I'm starting to slow down as I move forward, as an example. Now, one of the things that's very convenient for us is that when we model things, we do tend to model things as being single points. There's this sort of like little footnote here, because why do we care about just a single particle? I mean, particles are teeny, tiny, tiny. We care about big things. Maybe we're in astrophysics. I want to know, what is the sun, That's not a particle. But in terms of practical application, we can actually model things as basically small, tiny particles which are really heavy, sometimes very, very heavy. All right. So here we go. We'll do some examples. The location of an object at time t, where t is measured in minutes, is given by s of t equals 13t squared plus 2t e to the t, and that's measured in meters. Find the velocity and acceleration of the object at a given time t, and make sure to include units. I will say that I have a tendency not to include units unless I'm told. However, make sure that if you're told to put units, you put the units. Because if you're instructed to put units and you don't, you'll lose points. And our goal is we want to get all the points. Got to get them all. Only then can we become a calculus master. And you're probably like pessimistic. No one can become a master, but we know from recent events that after just a mere 22 years of work, Ash Ketchum, he got them all, and he's a master now. It won't take you 22 years. You'll get it faster than that. All right. So, here we go. So, our position, s of t, is 13t squared plus 2t e to the t. So, find velocity. Well, that really means we find the derivative, s prime of t. What's the derivative of 13t squared? 26t. What's the derivative of 2 times t times e to t? Well, what rule do we need? Product rule, because there's t and there's e to the t, and they're producting, multiplying. All right. So, derivative of 2t, 2 times e to the t. So I like to do the derivative of the first times the second, plus the first times the derivative of the second, derivative of e to the t, e to the t. All right. So that's s prime of t, and we'll make a note that's v of t, because the first derivative is velocity. All right, what's s double prime of t? Well, take the derivative of the derivative. Derivative of 26t, 26. Derivative of 2e to the t, 2e to the t. Derivative of 2t e to the t, well, it's just like before. Product rule, derivative of the first times the second, plus the first times the derivative of the second. All right. And what is this? S double prime of t we call acceleration. All right. Now, we could simplify if we wanted to. There's not much to do. I mean, there is one thing. 2e to the t times 2e to the t is in fact 4e to the t. But as far as the functions go, these are the functions. So, all right. What haven't we done? We haven't done units. Now, one of the things I'll point out is I tend to not do units in my computation because I know that calculus works beautifully in that the units will be what we expect, especially if we use our d notation. So if we think about what velocity is, this is the change in position with respect to time. So what are the units? Well, I look at the units of s, which is meters. And I'm going to divide it by the units of t, which is minutes. Yeah. Sneaky, I put it right there where people would not look. So, not everything has to be meters per second. You physics people, you. Okay, acceleration. In terms of the d notation, how do we write that? d squared s over dt squared. And the units are, well, you look upstairs and say, I see a single s. Well, what are the units of s? Meters. So it's just a single set of meters over, now look downstairs, minutes squared. So in other words, if you follow the notation with this format, d squared s dt squared, you just say, okay, units of s over the units of t squared. And there you go. You're guaranteed the units will work out because it's set up to work out, which is nice. All right, and that's the answer. Good. So, here we go. A projectile is fired into the air and lands in a valley. And its height in feet above the firing is given by s of t is negative 16t squared plus 48t, where t is measured in seconds. So I should probably sort of show you the picture. So there's this little projectile launching machine. Okay, so here I'm launching a projectile. So there's my projectile. Now what's going to happen is the projectile is going to go, and then it's going to eventually land down here somewhere. All right, so what do we have? There's sort of, you might think of, okay, isn't this two-dimensional, where there's this left, right, and up, down? And for right now, it's just saying the height is this. So we don't care about the actual motion in the horizontal direction. This is the vertical. And we're just going to focus on that part. So where it's fired from, this is at a height of 0 feet. Because, well, what happens when you plug in 0? You'll get 0. All right. So there's a question, what's the maximum height above the firing point reached by the projectile? Now, we can do this question in two different ways. We can do a calculus way, or we can do a non-calculus way. Which do you prefer? Calculus. All right. Sounds good. I mean, you're paying for calculus lessons. Okay, seems reasonable. All right, so here's the calculus way. We think about what's happening. So what's happening is initially it's going to go up, and then it's going to go down. So if I want to understand where it reaches its highest point, I want to say, okay, if I think about the sign, so when s prime of t is positive, I'm going up. When s prime of t is negative, I'm going down. So what I want to do is I want to say, well, when do I transition from up to down? That's the high point. So what is s prime of t? Negative 32t plus 48. So that's s prime of t. So where am I interested in? I'm interested in when it's 0. Because if I'm transitioning from a negative number to a positive number, there's this fun thing called the intermediate value theorem that says you have to pass by 0 if you're going to go from negative to positive. So when does negative 32t plus 48 equals 0. Well, if you move the negative 32t across and then divide by 32, you'll discover that says t should be 48 over 32. But you can write that more simply because it turns out these are numbers that involve multiples of 16. So this is the same as 3 over 2. And if we throw in units, we can say seconds. Why seconds? Because it says seconds. All right, so that's the time. Now, is that the answer for part A? No, because notice it said, what's the maximum height? What have we discovered? We discovered when it reaches that maximum height, but we haven't discovered what maximum height. So how do we finish the question? We plug it in. So the max height was going to come from when we plug 3/2 into our function. So that's negative 16. 3/2 squared, well, I'm going to go ahead and write that as 9/4, but this is 3/2 squared, plus 48 times 3/2. So the 16, 4 goes into 16 4 times. 4 times 9 is 36. 2 goes into 48, 24 times 3 makes 72. 76 minus 32 makes 72 minus 36. I can say those words. That's 36. 36 what, by the way? Feet. All right. Now, is that the answer for part A? Yeah, that is. Now, in case you're wondering, how do you do it without calculus? Well, it turns out we can cheat a little bit because this isn't just any kind of function. Do you recognize what this function is? It's an upside-down parabola. So you can say, hey, you know what? I could write that function as, let me factor out negative 16. That's t squared minus 3t plus a very large mysterious gap. And I say, you know, I like squares. And I'd like to write just the expression so there's one single t. So I come and say, what can I do? Well, what can I do to help you be completed? I want to complete my square. T squared minus 3t, what would I need to add here so that this could be a perfect square? What would I need to do? You would divide the middle term by 2, negative 3/2, and then square it, means you'd add 9/4 here. Add 9/4, subtract 9/4. So this becomes, if you rewrite this term is negative 16, t minus 3/2 squared. Negative 16 times negative 9/4. Well, 4 goes into 16 4 times. Minus minus makes plus. So this becomes 36. And now you say, all right, so that's just another way to write the function. I peak out when this term is 0, because otherwise I'm subtracting something. So I peak at t equals 3/2, and the max height would be 36. Now you might say, cool, I don't need calculus. I could just get by life with algebra. You probably could do pretty well in your life. But this relies on the fact that you have a very simple function. We want to get to the place where it says, you don't have to rely on the fact that you have a simple function, because we are better than that. We can solve all the problems. All of them. All right, there's a part B. So the projectile lands in the valley, 160 feet below the firing point. What is the speed of the projectile when it hits the valley floor? Okay, so first off, it launched from 0 feet. Where does it land? What's the height? Negative 160. Now, if I'm after this, it says, what's the speed? Well, what do I need to find? I need to find the velocity and take the absolute value. If I want the velocity, what do I need to do? Take a derivative. All right, so we already have the derivative. So s prime of t, again, that's negative 32t plus 48. So we just take the absolute value and we're done, right? Well, no, what's wrong? What are we missing? We got to plug in. We got to plug in a time. Which time do we plug in? Yeah, we don't know yet, right? We've got to figure that out. So what we do is we say, okay, our height, negative 16t squared plus 48t, has to equal 160. Well, move things around. Say, let's move these t terms to the other side. 0 would be 16t squared minus 48t plus 160. Am I doing that right? All right. No, sorry. Yeah, this is a negative 160 here. There we go. I knew something was wrong. All right. Now what? Divided by 16. 0 should be t squared minus 3t minus 10. Now what happens? Well, hopefully it factors. Does it factor? He says as he writes it down like it factors. It does factor. T minus 5, t plus 2. Because negative 5 times 2 gives negative 10, and negative 5 plus 2 gives negative 3. So, when do I hit the valley? Well, it looks like it's either 5 or negative 2, but negative 2 would be if you were running backwards in time. And most physics problems, they don't like that, so it's not the negative 2. So, what do we do with the 5? We come back up here. So we say, well, what's s prime of 5? All right, that would be negative 32 times 5 plus 48. Well, 32 times 5, that turns out to be negative 160. Just a coincidence, don't read too much into that. Plus 48. Negative 160 plus 48 is, of course, that is correct, negative 112. Good. All right. So, is this our answer? No. There's two things we need to correct. What do we need to do? Absolute value, because we want speed, which means it should be an absolute value. What's the other thing we need? Units. So our correct answer is 112. What are the units? Feet per second. Feet per second. That's how fast our projectile hits the ground. All right. Okay. Well, let's talk a little bit more about motion. So suppose you have a particle on a line, and we're just going to be really simple, straight line. We can think of it as moving left and right. And so our particle is somewhere. Maybe our particle is right here. We say it's at rest, which means it's not moving, if its velocity is 0. So there's velocity positive. What is that? Well, velocity is positive. It means that it should be increasing. So as we change time moving forward, if our velocity is positive, our position should be positive. And so we move to the right. If our velocity is negative, that says as time changes, in other words, time goes forward, time increases, then our position decreases. It goes more negative, so we go that way. So again, we can talk about orientation. So here, we're moving this way if velocity is negative, and we move that way, velocity is positive. Orientation is very important in mathematics, and the further you go, the more important it gets. So, we have a question. The position of a particle at a given time, t greater than 0, is given by the following expression: 11 times the 4th root of t minus 3 times the 4th root of t to the 5th e to the t. When is the particle moving to the left? When is the particle moving to the right? And where will the particle be when it is at rest? So, 3 questions. So, notice the first 2 questions are really related to each other. When is the particle moving to the left? That says we need the velocity to be negative. When is the particle moving to the right? We need the velocity to be positive. So we should probably say, what's the velocity? Well, let's start. We have s of t. Now, notice the notation here. 4th root of t. Fine notation if you were hanging out with with algebra people. But we're calculus people. So we're going to write it in a calculus way. So we're going to write that as to the 1/4 power. Similarly, this 4th root of t to the 5th will become t to the 5/4. And then we have e to the t. So we have 2 things multiplying together. So to find the velocity, we're going to take the product rule. So the velocity says you take the derivative of the first term. So that would be 11/4 times t to the minus 3/4. And then here, you're going to take minus 15/4 t to the 1/4 and multiply it by the original function, e to the t. And from there, we take the first function, 11 t to the 1/4 minus 3t to the 5/4 times by the derivative of the t. And the derivative of the t is e to the t. We want to clean this up because we want to understand things like positive, negative. So we say, all right, they both have e to the t. Might as well factor that term out. So if we do that, let's see, what do we have? We have 11/4 t to the minus 3/4 minus 15/4 t to the 1/4. And then here, plus 11 t to the 1/4, and then minus 3 t to the 5/4, and all that times e to the t. The middle terms we can combine, because they're both t to the 1/4. So 11, we can rethink of this as 44/4. So if I take 44/4 and I subtract 15/4, well, we're left with something fourths, and the answer is 29/4. Okay, so this is really 29/4. Now, how do we simplify? Well, let's do the following. I'm going to pull out a fourth because I don't like fractions, and I'm going to pull out the lowest power of t. So that's t to the minus 3/4. And now, notice that really the highest power of t is back here. That's t to the 5/4. And I always like that to have a positive coefficient. So I'm going to go ahead and also pull out a negative. So again, I'm pulling out negative 1/4 t to the negative 3/4. So let's start back here. We pulled out the negative, and then we haven't pulled out a 1/4. So then what's going to be left here is I have to divide by a fourth, which means that there's a 12. And the exponent, we take 5/4 subtract negative 3/4, and if you do that, you'll end up with t squared. Then in the middle term, we pulled out the fourth, but we didn't get, there was a positive, because the minus becomes a minus 29. Now what's the exponent? Well, see, this is t to the 1/4. We pulled out t to the negative 3/4. 1/4 subtract negative 3/4 will leave us with t. And here, well, we pull out the fourth, but there's no minus, so there's a minus here. And we pull out the t to the negative 3/4, so we're left with 11. All right, and then we have e to the t. Now, if we've lived a good life, oh, I really hope so. I really hope we've lived a good life. Then what should be true? Well, what should be true is that that part should factor. Does it? Well, if it does, what would it have to factor as? Well, there's not many ways to break up 11. So it has to be 11 and 1. Now we say, all right, well, what about the 12? Well, 12, there are a lot of ways to break it up. 1 and 12, 2 and 6, 3 and 4. But notice, there's something times 11 and something times 1. So something times 11 has got to be close to the 29. So if we think about it, okay, well, what times 11 is close to 29? The answer is, if we're given that 1, 2, 3, 4, and 6 are 12, are our options, probably 3. So we're going to guess, make this a 3, which makes this a 4. And if we do that, does it work? 12t squared minus 33t. Oh, whoops, there should be a plus here. 12t squared minus 33t plus 4t minus 11. It works. Wow, we've lived a good life. All right, now from here, what happens? Well, we're trying to understand what changes, and we want to understand the signs. Now, we only care about times greater than 0 because the assumption says time is greater than 0. So this part right here will always be this 1/4 t to the negative 3/4. It's always positive. This is a negative here. The 3t plus 1, always positive. The e to the t is always positive, which says really, it comes down to this. What's happening to 4t minus 11? Well, the key, the interesting point, would be at 11 over 4. Why? Well, because that is when you plug in, you get 0. So, we can see the following. So suppose for a second t is below 11 over 4. So it's a small number, like 1. 1 is below 11 fourths. What will happen is you'll get a negative number here. Positive, negative, positive, positive, negative. That says v of t will be positive, so move to the right. So below 11 fourths, or if you like, between 0 and 11 fourths, whoops, not right, just right. I missed International Speak Like a Pirate Day by 1 day. That was yesterday. All right, what about above 11 fourths? Well, if we're above 11 fourths, pick a number like a billion. 4 billion minus 11 is positive. Positive, 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 negative. All right, that says v of t is negative, which means we move to the left. To the left. Okay, so we've answered the first two questions. We are moving to the left if we're above 11 fourths, and we're moving to the right if we're below 11 fourths. So that just leaves one time. So at t equals 11 fourths, the particle is at rest. All right, well, So, but remember, what's the question? It's not a when, it's a where. So how do we get the answer? So to get the answer, we plug in 11 fourths. So we say position, when it's at rest, will be s of 11 over 4, which is equal to 11 times the fourth root of 11 over 4 minus 3 times the fourth root of 11 over 4 to the fifth times e to the 11 over 4. And what do we do with that? We box it. Done. We don't have to simplify it because they didn't ask us to simplify. All right. Good. So what's the takeaway? So we can think about how velocities are changed. Negative velocity, negative change. Our value of our output goes down. Positive velocity, positive change. Value of our output goes up. And 0, sort of that sweet spot. In fact, the 0, when the derivative is 0, is going to be a really important idea. And we're going to get quite a lot of useful information about that as we move on in our course. All right. So the last idea to talk about is economics. We're going to do a little bit of economics. And I'll tell you something you may not know. I actually have a degree in economics. And I was raised in a house. My dad is an economics professor. So it's in my blood. So I know a little bit. Not much, but just enough. So suppose you want to make decisions about how you set production. Now, your goal is to say, I want to make a lot of money. So that's a good goal, especially if you're in business. So what you do, the question is, let's look at how much it costs for you to make your last unit. So, what we call the marginal cost. And why do we care about that? Well, oftentimes when we're trying to figure out cost and revenue, it's hard to figure out, well, where's the right place to set quantity? What's the right thing? So you might say, well, maybe you should make it so that quantity is such that the cost equals revenue. No, that's a terrible. That's cost equals revenue means no profit. No. We want to look at something better because, we want profit. We want to stay in business. So the idea is, let's look at the marginal cost, which is the cost to make one more unit. So I'm making some units. I say, all right, well, the cost to make one more unit, it's the cost of plus one more unit minus the cost of the number of current units, over 1. In other words, you can think of it as the change. Well, that looks a lot like a derivative. So what we do is we model it by the derivative. We say, okay, the marginal cost is the derivative of cost. And the marginal revenue, well, that's how much money we get if we sell one more. All right, well, now, where do we produce? When we think about the last unit, now a couple of things could be true. So the marginal cost could be below the marginal revenue, which means that if we produce one more unit, it would cost less than the amount of money we get. In other words, that's a good unit. We should produce, so we should increase our output. If the marginal cost, the cost to produce that last unit, is above the marginal revenue, that means we're losing money. So making that extra unit is a money loser. So we should not do that. We should decrease our revenue. Sorry, not our revenue. We should decrease our quantity. So where's that sweet spot? Well, what we don't want cost above revenue. We don't want cost below revenue. So that means so its cost is at revenue. So when the marginal cost equals the marginal revenue, there's no incentive. So that must mean we're pretty happy. Because where else would we have no incentive to change? We have no incentive to change when we're making as much money as possible. So that's a good idea. All right, so we have an example. Suppose we have cost, and our cost function, C of Q is 30Q minus 22 times the square root of Q. And our revenue function, R of Q, is 40Q minus 2/3 Q to 3/2. Determine the marginal cost, the marginal revenue, and at what point should we set production? All right, and then there's a second question. Let's get to that second question later. So marginal cost is just a fun way of saying the derivative of the cost. So we take the derivative. And remember, square root of Q is really Q to the 1/2. The derivative of 30 times Q is 30. Then we have 22. The derivative of Q to the 1/2 is 1/2 Q to the negative 1/2. So we can simplify this by saying this is 30 minus 11 over square root of Q. Marginal revenue, that's the derivative of revenue. So that would be 40. The derivative of 40Q is 40. Minus 2/3 times 3/2, because the 3/2 power comes down, Q to the 1/2 power. Well, that would be 40 minus 3's and 2's cancel, square root of Q. All right, so that's the marginal cost, marginal revenue. Now, where do we set production? We need these things to be equal. 30 minus 11 over square root of Q, at best equal 40 minus square root of Q. So let's do what we often do. Well, let's move everything around. Let's move everything over to this side. So we can get that the square root of Q minus 10 minus 11 over square root of Q equals 0. And if you get rid of that square root of Q, which you can do by multiplying through by square root of Q, you get the square root of Q quantity squared minus 10 times the square root of Q minus 11 is equal to 0. Now, one thing that's not necessarily immediately clear, you might be tempted to say, oh, square root of Q squared is just Q. The reason I want to write it this way is to sort of say, wait a second, is this a quadratic? Because it's a quadratic. You see, if I think of my variable as being square root of Q, I could think of this as y squared minus 10y minus 11. And I say, that factors. In fact, how does it factor? Y minus 11 and y plus 1. You can check. Y squared plus y minus 11y. So plus y minus 11y is minus 10y, and then minus 11. So what does this tell us? It tells us that capital Y, which again was just a placeholder for square root of Q, is either 11 or negative 1. But square roots aren't negative. Now, let me be careful there, because oftentimes people say, wait a second, I thought things like square root of 4 is plus or minus 2. No, the square root of 4 is 2. The reason we put plus or minus is when we say, when we solve for something where x squared equals 4, we have to have both possibilities. The square root function itself only produces a positive number. Well, that means there's really only one candidate, and therefore, to find it, we square both sides. We say, okay, we should set production at 121 units. So there we go. There's our marginal cost, our marginal revenue, and our production level. There was one more question. Should we produce? Now, you should think, well, wait a second. Don't we definitely want to produce here? Here's the thing, is it's quite possible that we are in a situation that even under the best circumstances, we can't make money. So how do we know if we should produce at all? We know that this is the best place to produce, but how do we check? And the answer is, you take this information and you plug it back in. And if you do that, well, what you do is you check what happens when you plug R of 121 minus the cost of 121. See, if this is a negative value, don't produce. You're going to lose money. If it's a positive value, produce. You'll make money. And then life is good. And we like it when life is good. And what does it turn out to be? I don't know. So, for that one, I'd use a calculator for this one. Well, okay, all right. Let's do this properly. What do we get? We'll just do this on a scratch page. All right. No one has to see us doing our little scratch work here. All right. So, we're taking R of 121. We're going to subtract the cost of 121. Now, it might be helpful to just note, we can save ourselves a little bit of work, revenue minus cost in general. Well, we can save 40Q minus 30Q is 10Q. And then we get minus 2/3 Q to the 3/2. And then minus makes a plus 22 square root of Q. So, when we plug in 121, we're going to get 10 times that. That's 1,210. That's pretty promising. 22 times square root of 121. Well, that's, if we think about it, square root of 121, this is going to become 11. So it's 2 times 11 times 11. That means that we're going to add on to that an extra 242. Because 121, that's plus 242. And then we're going to subtract off 2/3. Then we have square root of Q, which is square root of 121, which is 11, cubed. Now, square root of 11, what is that? Well, that's 1,331. And we're going to multiply that by 2/3. Well, and we want to compare that to, over here, 14,052. Well, if I take 1452 and I subtract 2/3 of 1331, look, 1331 is already smaller than 1452. Multiplying it by 2/3, that's even smaller still, which means, yes, this is positive. Produce. We're going to make money. And of course, when we make money as a business person, the world is a better place. At least that's the idea. All right. Well, there's our little bit of economics.